Let's talk about label propagation for node classification. It is an operating system process where it has several states to classify to understand. Now we are gonna use this label propagation in a real-time scenario, metro station scenario. This is a scenario which I have taken. So first, let's talk about metro station analogy. Okay, let's take a simple picture. Imagine a crowded metro station. Every passenger here is like a node in a graph, and the badges they wear are the labels. Some people already have badges, while new one comes in without any. Now, as they stand on a platform, they look at the people around them and slowly decide to wear the badge that most of their neighbors are wearing. Over time, everyone settles with the badges. Uh, that is basically how label propagation works. And to make it easier to understand, I'm connecting this process to operating system states like new, ready, running, waiting, and terminated. So these are the states which we are gonna see in this PPT. So the next is how label propagation works. Okay, it's actually simple. The algorithm starts with a few nodes that already have labels, while the rest are unlabeled. Then, in each round, every node looks at its neighbor and picks the label that most common around it. This keep happening again and again until nothing changes anymore. At that point, we say that labels have converged and the process is finished. So it's basically the one without the labels look around its neighbor and checks who has the most labels or badges common, and they choose that badges to wear them. So this is how it works. The label propagation works. So next, mapping to OS process states. Now let's connect this to operating system states. In the new state, it is like a passenger entering to the metro. Some already have labels, some doesn't have labels. In the ready state, the passengers are just waiting and watching others. And in the running state, they are actually picking up the badges. They update themselves from their neighbors. Then comes the waiting state, where they pause while others update and then go back to the ready for the next round. Finally, in the terminated state, everyone is stable. Nobody is changing labels anymore, and the process ends here. So, as for visualizing a label spread, okay, let's take an example here. Imagine six nodes in a graph. At the start, only two nodes are labeled red. Uh, in the first round, their neighbors become red, and in the next round, even more nodes changes to red. By the third round, all the nodes changes to red, and the algorithm stops. So you can see how quickly labels can spread across the graphs. Okay, so next is about challenges in label propagation. We are going to see what are the challenges we face in label propagation. The first problem is that it assumes connected nodes are similar. That is called homomorphology assumptions. But in many graphs, the neighbors can complete different and then it doesn't work well. The second problem is dependency on initial labels. If you start with the wrong nodes label, the final result may not be accurate. And finally, sometimes a node keeps switching labels back and front before settling. That oscillation, that is an oscillation, and it can slow the whole process down. So these are all the challenges we are facing in label propagation. And the last is about integration with machine learning. That like how we are going to integrate this label propagation with the machine learning concepts. So even with these problems, label propagation is still a popular baseline method for semi-supervised learning. It is mainly focused on semi-supervised learning rather than supervised and unsupervised learning. But today, Graph neural networks or GNN takes this idea much further. Instead of just following fixed rules like majority voting, GNN actually learns how much weight to give each neighbor. That makes them way more powerful and adaptable. So in a way, GNN are like the modern, smarter version of label propagation. Thank you.